Today's video is going to walk you through how to do some basic two-dimensional vector addition and subtraction, because while we're at it, let's do it. So somewhere around page 40 in your workbook, I would like to say it's page 40, but odds are good. Depending on what year you watch this video, I've made some tweaks to the workbook. And so it's probably still going to be around somewhere page 40, but you'll probably find this page right here where it kind of walks you through some very basic, hey, can you add and subtract, and how do you do this? So it should be the same vectors, A, B, C, D, E, F, G, that you probably worked with in the previous couple of lessons. It's just now we're going to add them together. This work page has an example problem given to you right on the actual page itself for you to kind of look at and sort of figure it out on the fly. But I'll go one step above and beyond, and we'll go and do one together for the purpose of this video. So I'm just going to make one up. I'm going to say we're going to take vectors A plus D and figure out what that is on the left, and then to the right, I'm going to take vectors A minus D, and I'll show you how that's done on the right. So vector A is right here. Okay, if we take a look at vector A, recognize that it is going to go from a starting location. It should be written down in terms of 1, 2, 3, 4 units to the left, sorry, to the right. So if I write vector A down, it is written down in rectangular components as 4 meters, comma, because I went 4 to the right. And I'm going to go 1, 2, 3, 4, 5, 6, 7. It is located 7 meters up. If I was smart, I considered at least 2 sig figs. So I'll call it 4.0 meters and 7.0 meters. So that's what A actually is. Vector B, I'll make in blue. Or sorry, not B, I'm doing vector D. Vector D is over here. I'll still draw it in blue. So vector D is in blue. I typically count my x's first. So 1, 2, 3, 4, 5, 6, 7. So it is 7 squares to the right. So vector D is equal to 7.0 meters, which is pointing to the right. And it is going to be pointing down 1, so start from this location right there, pointing down 1, 2, 3, 4 meters going down. And so that makes a vector arrow going down. So because it is going down, then I have to write it down as a negative 4.0 meters. Now, vector addition of two-dimensional vectors is pretty straightforward if you have them broken down into x and y. And I luckily wrote them down one above the other, just to kind of point out that it's actually not too bad to add two-dimensional vectors as long as they're in x and y component form. So if I'm going to add these vectors, to get vector s, all I really have to do is add the x value above to the x value below. So essentially walk these two x values down. So I'm going to add the 4 to the 7. So 4 plus 7, last I checked, should be 11.0 meters. And when I take the base values of my y components, if I go down 7, I'm going to add a negative 4. That's the same thing as saying 7 minus 4. And so 7 added to a negative 4 should just be a positive 3.0 meters. And so effectively, I have just determine what my x and y value is supposed to be for my vector s. So that's just figuring out what the x and y values are. Now to draw them is just a little bit more complicated, not too much more. So what I would recommend you do is you just start at a single location. I'm going to start at this point right here in red. Let's see here, I'm going to start right about here. Right, any random point, ideally somewhere near the center vertically, because I believe, again, we have to go 7 spaces up. And then I'm going to switch to my straight line tool, if I can. And my straight line tool there, I'm going to select the color red just to be color coordinated. I need to more or less copy this out. I have to copy this vector right here, but down below. So I need to show how my vectors connect when I add the vectors. And so when I draw it out, I usually just look at it with my eyes and go, okay, this vector should be 4 squares to the right, 7 squares up. So then I count 1, 2, 3, 4 squares to the right, and then I count 1, 2, 3, 4, 5, 6, 7. That right there is my vector A. Right? Obviously, you're not going to be able to draw it that way with your pencil. You'll probably just, of course, with your pencil, just make little dots, 1, 2, 3, 4, to indicate the 4 spaces there. And then you'll just with your pencil from this location, count up 1, 2, 3, 4, 5, 6, 7 to get that location there. And then you just connect the dots and draw the red vector that you see in front of you. So that is vector A. When you add vectors, where the first vector stops, so that's where the vector arrowhead is there. So I make a new origin point at the head of the first vector. I then draw my second vector. So D, stick with the green, D is this vector here. And so this vector is, of course, we've already counted this once, it is 7 squares to the right and 4 squares down. So starting from this spot right here, I would count 1, 2, 3, 4, 5, 6, 7 squares to the right. And then I'll count down 1, 2, 3, 4 squares down. So if I get my straight line tool involved, I'm going to want to connect these 2 points together. So that there is vector D. So this is my vector D. Vector A is sitting right here. Now, normally when you put the labels right next to the vectors, you don't have to draw the vector symbols, just the magnitude. In other words, just the symbol A and D will suffice. Now, I've already solved this for this mathematically. I will use green as my resultant. So at this point, where my second vector stops, that is where my ending point is. And so when I connect the 2 dots, I want to begin my resultant vector at the very beginning where I originally started. So roughly right there, and I'd point my pencil with my ruler and connect those 2 points together because I want to end up exactly where I wound up. So that is this point right here. I'll draw in my vector arrowhead so it's a bit more obvious, right? Because the arrows that are attached to these straight lines aren't overly obvious. And so that is my vector S, right? That is my vector S. Now, according to my math, I should be 11 squares to the right. Bear with me. I'm going to count those. I'll use magenta for that. So starting from this point here, I should be 1. Sorry, I said left. I meant 11 squares to the right. Starting from this point, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sure enough, 11 squares. And I should technically be, to get to this spot right here, according to what the math I've already done, I should be 3 squares up above. So if I do that math, 1, 2, 3. How about that? So I have drawn my vector properly. So what you see that it's drawn in the red, blue, and green arrows, that is the graphical representation of a 2-dimension vector addition. On the left in numbers, that is how you would add your vectors together normally. It is a lot easier to add your vectors if you actually break it down into X's and Y's. So if it's written in polar format, you'll have to convert it to rectangular format. More often than not, the standard way of writing a vector is in polar format, and so therefore you're typically going to have to convert it into polar format. So I'm going to kind of point out what your assignment looks like. So this page here, you're more or less just looking to write it down in X's and Y's. So you're looking to write it down as rectangular format. And there's another page after that, but if I've copied and pasted what the next page looks like, it is another phys job page made by Dean Baird from California. It's basically taking the same question, H, add vector A plus vector B, only this time it's not graphically. So you're going to do what I did, the original. I'm just going to add my X's with my X's and add my Y's with my Y's, and that's what I did on the left side of the screen. The only difference is they want you to represent your final answer in the polar format. I haven't quite done that yet. It shows you on this page an example problem, but I'll walk you through an example that we're currently working on. So what we have here is our answer written down in rectangular format. Now to convert to polar format, you've done that once already, so hopefully it shouldn't be too much of an issue. So remember, we're going to use our Pythagorean theorem. So c squared is equal to a squared plus b squared, because we're going to take vector s and consider just the x component and the y component. So we just want to deal with that green triangle now. And if you draw like I just drew, English is hard, we've got ourselves a nice little right triangle. I'll redraw that down below. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, a bit of a delay. And then it is 3 squares up, 1, 2, 3. And so I'm not going to be very good with this. There we go. So that's kind of the vector I've got, just sort of redrawn. I didn't use a straight tool, so it's a bit of a bump in my line. Not the greatest. I would not typically allow that, but it's a bit more difficult on my screen. So I've got myself a nice right angle triangle. I've solved for this guy right here. This is 11.0 meters. This guy is 3.0 meters. Again, I'm just writing that off to the side because it's starting to look pretty ugly up here. I want to find my hypotenuse. This is the hypotenuse S. This 11 is my S value in the X. This 3.0 meters is my S value in the Y. And so if you're just doing basic math, c squared is equal to a squared plus b squared is good enough, because you would probably call this guy right here C, you probably call that guy there A, you probably call that guy there B. But we're going to write this down in physics terms. So S is equal to the square root of Sx squared, square drew an X. Sx squared plus Sy squared. Right, and we have our numbers, so it's just a matter of plugging them through. Right, X is our 11.0 meters. We will square that. Add that to my Y, which is 3.0 meters. We're going to square that. And then you take the square root. Okay, so 11 squared plus 3 squared. I'll write that down below. You'll probably end up with 11 squared is 121. 3 squared is 3 squared is 9. So 121 plus 9 will give me 130 square meters. So I skipped a step. I didn't show how I did that. Just you plug that into your calculator. And if you take the square root of 30 meters squared, 130 meters squared, you will probably get something pretty close to 11.4 meters. So that is the magnitude of my vector. Okay, so that is what the length of this hypotenuse is, right? So that's this hypotenuse length right there in the magenta or pink or whatever color you want to call that. So in order to write this down in polar format, I need to have a magnitude. I'll put it in a box, and I need a direction. So I still need this little angle right here. So again, as far as what's drawn on this triangle up top, oopsie, I don't know what happened there. What's drawn on this triangle up top, I'm looking for this angle here. I don't care about that angle there. I always want my angles measured from either an X like that, or from a Y, which would be all the way up there. So I'm going to use this little X here and measurement. So this theta there is the angle I'm going to look for. So to find angle theta, I need to take the inverse tan function of my opposite side divided by my adjacent side. So my opposite side is going to be my Y component. My adjacent side is going to be my X component. So this is going to be Sy divided by Sx. So if I plug this stuff through, I should have the inverse tan function multiplied by 3.0 meters divided by 11.0 meters. So if I take that tan inverse function, I will probably get something pretty close to, what happened? I'll probably get something really close to an angle of 15 degrees. Okay, so when I write this finally, so that means right here, I'll scroll up a little bit. So that means this little angle, I'll retrace this right there. That little angle, I'll redraw it in, I don't know, blue, I guess. I'll redraw that. That right there is 15 degrees, which means this right here should be a 15-degree angle. All right, I did some rounding. I just rounded up to a whole number. So to write this down properly in polar format, my vector S is equal to its magnitude. So that's this 11.4 right there. So that 11.4 is the hypotenuse at an angle of 15 degrees. So I happen to be in quadrant 1. So if you remember quadrant 1, if I draw an axis here, quadrant 1 is up here, quadrant 2 is over here, 3 is down there, 4 is down there. Let's get a little congested, so I won't write those. Because I'm in quadrant 1, I can just straight up write it as 15 degrees. If I was in quadrant 2, I would have to add some value to it. But you guys know how that's done. I think we've done a couple in class, so you should kind of know what to do there. And that's more or less how you would solve for this one example. So that's vector addition. Now let's do vector subtraction. I'm going to take the exact same vectors, vector A and vector D, only this time I'm going to subtract them. And I'm mainly using the same two vectors just because we've already solved for them. We already know what their X's and Y's are, and so there's not a whole lot of new information we need to get. I'll just do a quick little reminder. I'll erase them. So with vector A, we know that vector A is 4 squares to our right and 7 squares up. We've already established that. And so I'm going to write that down as vector A is equal to 4.0 meters in my X, 7.0 meters in my Y. My vector D that I'm now subtracting is equal to the negative of, so vector D, of course, looks like this. I've got 7 squares to my right, and I've got 4 squares down. That's what we decided earlier. So I'm taking the negative of 4.0, sorry, I was reading a different line. Its X value is 7.0 meters. Its Y value is 4 meters going down. So once again, that's negative 4.0 meters. So I'm taking a subtraction, which means this negative symbol applies to my 7 and it applies to my negative 4. So technically, what I'm actually doing is I'm taking 4.0 meters to my X and 7.0 meters in my Y. And I'm actually adding to it. I'm only pointing this out for, you'll see why I'm changing this in a second. I'm actually adding to it a negative. So instead of saying negative, I'm adding to it a negative 7.0 meters, comma, and I distribute this negative over to the 4.0 meters. And the reason why I'm changing the way I'm representing this is because technically, when you subtract vectors, you're technically adding the negative. And so when I say you're adding the negative, even though D looks like this, negative vector D, so that's the opposite, basically takes the arrowhead and points it in the exact opposite direction. So negative vector D, if I draw it just right underneath of it, is technically 7 squares. I'll erase that. 7 squares to the left. 1, 2, 3, 4, 5, 6, 7. And it is 4 squares up. 1, 2, 3, 4. All right, so the negative vector D is actually this line right here. It's the exact same magnitude, it's the exact same length. You want to think of it as a length. It's just pointing in the exact opposite direction. So that's what happens when you subtract a vector. The second vector gets flipped so that the arrow is pointing in the exact opposite direction. I need to use that when I do my diagrams, but otherwise, if you're just doing the math with the numbers, you guys can figure the numbers out. 4 minus 7, well, most of us can do that. You should end up with negative 3.0 meters. So this is vector t in the end. We end up with negative 3.0 meters in my x value. And as far as my y is concerned, 7 minus negative 4 is the same thing as saying 7 plus 4. And that will give me, once again, 11.0 meters. So that's what I do in that case. So vector subtraction is really no different than vector addition. You just want to think of it in terms of adding a negative rather than just a straight up subtraction. So to draw them out, we are going to basically do the same thing. So I'm going to start with A, vector A. I'm going to draw right about here. I'll start this right about here. So vector A is going to start there. I'm going to draw vector A the exact same way I did before. I'm going to move 4 squares to the right. So starting from my origin, I got 1, 2, 3, 4 squares to the right. I'm going to go up 7 squares from this spot right there. So 1, 2, 3, 4, 5, 6, 7. And now I just connect my vectors. Draw this in red again. So there's where vector A is. Right, that would be vector A. I don't put the arrow above the A when I draw it right next to the actual arrow. Now, actually, I'll put A over here. There's A. Now, vector D is supposed to go 7 squares. So I'm going to use vector negative D. So if I'm subtracting vector D, that's the same thing as taking vector A added to the negative of D. And so I've drawn up above what the negative of vector D looks like. It's going to be 7 squares to the left. Oh, I hope I gave myself enough room. It's going to be 7 squares to the left. So therefore, it's going to be 1, 2, 3, 4, 5, 6, 7. I'm drawing right on the edge. That probably wasn't a smart decision, but here we are. And I had to go 4 squares up. And so therefore, I need to go from that spot 1, 2, 3, 4. And I found the bare minimum that I can draw on this. So that's pretty safe, actually. So I'll draw my next vector arrow to connect like so. And somehow I wound up by chance in the top of the left-hand corner of the screen. That was not planned. That's not a big deal. So this is going to be vector D. This is vector negative D technically. All right, this is now vector negative D. And so I've connected my 2 vectors. The last thing I need to do is connect my resultant vector and my resultant vector, which I was drawing in green. I'm going to start at the very beginning like I did last time, and I'm going to point to the very ending. All right, so that vector is pointing up and to the left. And so if I consider what my answer was from before, it should technically be 3 squares to the left because it's negative, and it should be 11 squares up. And so I'll just double check that starting from the beginning here. 1, 2, 3. Sure enough, that checks out. 3 squares to the left. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 squares up. So that is my resultant vector. So it ends up being quite the steep right angle triangle. Okay, I'm going to draw that somewhere else just so it's off to the side. So 1, 2, 3. So there's the 1 vector arrow there, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I should probably use a straight line tool if it's going to be this long. Otherwise, it's just going to look sloppy. You can't have sloppy work. All right, so that is my resultant vector. I just drew it off to the side. Basically, just copied the exact same vector. It just looks a bit neater when it's off to the side there. So that is my resultant vector t. So that is vector t. Over here is my t in the y. Over here is my t in the x. I've got vector arrowheads pointing in the correct directions. Except for this down below, or that. That is t in the x. All right, so now I've got it written down in terms of x and y. The next step is to do Pythagorean theorem again. We want to find the actual length of t. So I'm going to take a bit of a shortcut here because if you notice from the previous question, I've got the same numbers, 11 and 3, 3 and 11, one's negative. That's not a big deal because realistically, if I plug them into the exact same scenario over here, I'm going to get the exact same magnitude. It just worked out that way. Actually, I probably shouldn't cut corners. I'll show you what we do. My t is equal to, again, Pythagorean theorem. So that's going to be t in the x squared plus t in the y squared. So if I plug in my terms, I've got the square root of t in the x. Oopsie, what am I doing? I've got the square root of negative 3.0 meters. I'm going to square that. I'm going to add that to 11.0 meters. And again, I will square that. 11 squared should be 121. 3 squared should be 9. Even if I have that negative involved, when we square negative, it becomes a positive. These two together is going to give me the same 130 meters squared that we got before. So now I'll cut a corner and just say t is going to be the same 11.4 meters. It just worked out this way. So that's not a big deal. Okay, so I added those two vectors together and I got the same magnitude, but we can clearly see this new vector is pointing up and left. So we're probably not going to get the exact same numbers. So if I do the inverse tan function now, okay, so if I do the inverse tan function, I'm going to do basically the same thing. So theta, new value here, theta is equal to tan -1. So I need to get the angle to write it in proper polar coordinates. So that's going to be my opposite side divided by my adjacent side. So if I'm going to find this angle right here, I usually like to measure my angle from my x. And so because of that, my angle is going to be from my y divided by my x when I punch that through. So I'm going to take the tan inverse function. Now, if I actually plug these numbers through, I should use the number 11.0 meters, all divided by 3.0 meters. So when I take the inverse tan function, it is going to spit out for me 74.7 degrees. Oops, forgot one thing. That's going to spit out negative 74.7 degrees if you use the negative. Now, I don't often use the negatives when I do my trig functions. I usually just make everything positive. So I'm going to retract that statement. Let's undo that. Let's undo that. And the reason for that is you're going to get the same numerical value. And what I expect out of you guys to recognize that, okay, that angle there is 75 degrees. Typically round it to a whole number when you're all said and done everything. However, the actual angle is not 75 degrees. So we have technically measured and calculated this guy up here. Realize it's really small and getting kind of cramped. That is 75 degrees if we're measuring from the axis that is going to the left. Now, when it comes to Cartesian coordinate system, I'll kind of redraw this using red. When it comes to Cartesian coordinate system, if my angle is going up and left like this, and I happen to know that this is 75 degrees, I actually have to make that measurement from 0. So I actually need to know what this angle is right here. I'm going to call it angle phi. So what you have to do at this point, angle phi is equal to, since I'm in quadrant 2, whenever you're in quadrant 2, you're going to take 180 and you're going to subtract whatever angle you just calculated. So in this case, we're going to take 180 and subtract 75. So 180 degrees minus 75 degrees. Right. And that should get us an angle of 105. That is the correct angle. So now I can finally represent my vector. My vector t, should be using green, color coordinate. My vector t is represented as 11.4 meters at an angle of 105 degrees, measuring from the right axis. If I happen to know that I'm measuring in north, south, east coordinate system, so the navigator coordinate system, I might want to call that 11.4 meters. I'll go back to the diagram for a brief moment. I am measuring from my, so this is my origin. I'd be measuring from my west axis and therefore going up towards the north. I think we did this a few times in class, or at least in the other video. And so you could represent this as west 75 degrees to the north. Word of caution though, if I didn't give you the okay to use north, south, east, and west, you're going to have to default to Cartesian coordinate system. I say that because some things might be going up in the air or down on the ground. If that's the case, the north, south, east, and west do not work. So I think this video is getting pretty long. You should know now how to, at the very least, add two vectors together and subtract two vectors together. So you'd be adding these two guys, then you're going to subtract the bottom three vectors. You should know how to do that pictorially as well as write it in terms of x's and y's. Right, there's a page after this that I'm going to skip. You guys should give it a try. And now you also know how to go from adding two vectors when you know the x's. This is the x's, you add the x's together, and you add the y's together. They kind of do it a little bit differently. I like to put my numbers above each other rather than side by side. And you know how to add them and finally put it back into polar coordinate systems. So you have a bit of work cut out ahead of you. This will take you a little bit of time. I'll probably make a second video here in the following days, or actually I'll probably just flow through this with you guys in class. The next page after that will take a little bit of extra effort. So that'll be the next video. If you have any questions, of course, send me an email. So try to get these 3 pages done. So this would be page 3. And then this would be page 1 and page 2 I don't have in this presentation because I didn't copy and paste it. So I think that starts around page 42, but I might be plus or minus a page. Okay, thank you very much. Have a good day.